So number 2 says we've got 3 parallel wires, each carrying a current of 2 amps. Okay. Now, if you just read the first part of the question, does everybody agree that it almost makes it seem like you have something like this? Does everybody agree? It says you have 3 parallel wires. But if you read carefully, it says the wires are oriented vertically. That looks vertical to me, right? But then if you read on, it says, and they pass through 3 corners of a horizontal square of side 4 centimeters. So I'm going to draw a square that is in the plane of the board. Okay. And at 3 of those corners, I have wires that run perpendicular to the board with current coming out of the board. That dot, remember, represents out of the board. So here I have 3 of these wires that are parallel. So does everybody agree that these wires would be parallel to each other? Does everybody see that? And you have them being perpendicular to the actual board. Does everybody see that? And which way is the current flowing? Out. Okay. So it looks like this. So here you have current coming out, here you have current coming out, and here you have current coming out. Okay, so the question is, what is the net magnetic field at the last corner? And we're going to make use of superposition. What does superposition say? Superposition principle. I can add the contribution from each individual wire. So I can treat them as separate entities. And then at the end I can add their individual contributions. Again, that is not a trivial statement. To derive that takes pages and pages and pages of very sophisticated math to do it. Okay? But it just so happens to be true. Okay, so what we can do is, and this is what I would recommend you to do every single time, to do it. Separate it out. So draw 1 wire at a time. That's the beauty of superposition. I can calculate the individual magnetic fields generated by each individual wire, and then at the end I can just add them up. Okay. So let's take a look at this guy. I want to find first the direction of the magnetic field generated by this wire, the direction, at point P. Okay. So how do I do that? Is that right-hand rule number 1 or number 2? Number 1, because it's field, not force. So I'm going to take my pencil, I'm going to put it perpendicular to the page, if you're doing it there, or my pen in this case, perpendicular to the board. I'm going to take my thumb, I'm going to put my thumb in the direction of the current, like this, and I'm going to curl my fingers around like I'm going to grab onto the pen, like this. So which way are my fingers curling? Clockwise or counterclockwise? Counterclockwise. So the field lines themselves, the magnetic field lines of that wire, are going to look like this. They curl counterclockwise to the wire itself, like this. Now, question. Magnetic field vector fields, are they source-free or do they have sources? They're source-free. What that means is that all they do is curl, they don't diverge or converge. Okay, they're source-free. So therefore, does everybody agree that it looks like this field line started here and it ended here? Did it really start here and end here? Or does it have no beginning or end? It has no beginning or end. It just curls around counterclockwise like this. So here I'm just not finishing up the loop like that. Okay, so those are the field lines or the field vectors? Field lines or vectors? The vectors. The vectors? Are they the field lines or the vectors, guys? Those are the lines. How do I draw the field vectors? They have to be tangent. So if I draw the vectors that are tangent to these guys, these would be the actual vectors. So take a look at this guy. Does everybody see how that vector is pointing straight up? Does everybody see that? So that vector is going to be pointing straight up. So in what direction is that? Does everybody agree that that would be in the j-hat direction? Okay. So now we can use the equation for the magnetic field of a wire, of a long straight wire. This is going to be the mu naught I over 2 pi r. Okay. That was the equation we derived in class. So we have B is equal to, and I'll call this B1 because it's the first wire. So mu naught, remember permeability of free space, so 4 pi times 10 to the minus 7. What's my I? 2 amps. Very good. Divided by 2 pi times, and the radius. This radius, this represents how far is the wire from point P. So that is actually given because it tells me basically the one I'm doing is this one. Does everybody agree that the one I'm doing in this case is the magnetic field point P due to this wire? Does everybody agree? Do I already know that distance? What's the length of each one of those sides? 4 centimeters. So does everybody agree that the radius in this case would be 4 centimeters, which is 0.04? Does everybody agree? So now, the 2 pi cancels with this guy 2 times. That's 4. It's 4 times 10 to the minus 2. So this is like 1 times 10 to the minus 5 Tesla. Okay. And in what direction would that be in, according to this diagram? Positive J. So that would be 1 times 10 to the minus 5 Tesla in the positive J direction. Okay, does everybody see how we got that? Everybody see that? Okay, so now I'm going to do exactly the same thing for the other guys. So let's do this guy. I'm going to do this guy now. This guy here. So where is point P in relation to that wire? At the bottom. Does everybody agree? So now, take a look. I'm going to use right-hand rule number 1 or 2? 1. So I'm going to take my thumb, put it in the direction of the current, curl. Which way are my fingers curling? Counterclockwise again. So does everybody agree that the field lines will curl around the wire counterclockwise? Does everybody see that? So I can continue some of those field lines. And it looks like this. Question. Do they begin here and terminate here? No, because that would be not source-free. This is a source-free field. A non-conservative vector field, in other words. So what happens is, if you draw here, the vectors that are tangent to those lines, what would you come up with for direction of the magnetic field at point P? Positive I hat direction. In other words, the positive X direction. That would be the positive X direction, whereas in this case it was the positive Y direction, which was symbolized with the J hat component. So what we can do, we can very simply use the same exact equation that we had here. So mu naught I over 2 pi r. So because it's the magnetic field of a wire still, so that's going to be 4 pi times 10 to the minus 7 times the current, same current, 2 amps, divided by 2 pi times, what would be the radius? Does everybody agree same distance? Does everybody agree 0.04? So that means that we get exactly the same. 1 times 10 to the minus 5 Tesla, but this time in the positive X direction, so we symbolize that with an I hat. That's the positive X direction. Alright, so does everybody see how we got these so far? Is everybody good? Okay, so now for the harder one. The one that is diagonal. Now we have to calculate the magnetic field generated by this guy. First, is the radius the same? Or is the distance from the wire to the location where I want to find the magnetic field, is that the same? It is not. That's going to be 0.04 times the square root of 2. Okay, just using Pythagorean theorem. So for that guy, the first thing that we note is that point P is all the way out here. Okay. Would you agree with me that immediately you can tell from right-hand rule number 1, just like in the other cases, that the field is going to curl counterclockwise for this guy? Does everybody agree? So that means that we're going to have a situation like this, just like before. But this time, does everybody agree that this field line will intersect this dashed line, this radius line, at a 90-degree angle? Does everybody agree? And does everybody remember why that is? Remember, to be able to explain why. That comes from the more deeper reason from the derivation itself. Remember, because it was a cross product, remember. So take a look. Does everybody agree that this angle with this field vector, which is tangent to the field line at that point, does everybody agree that they make an angle of 90 degrees? Does everybody agree? So now, here's the thing. What we're going to do is we're going to go ahead and say, all right, can I find the magnitude of that magnetic field vector? Can I do it? Yeah, that's the equation for the magnetic field of a long straight wire. So B3, that's going to be mu naught I over 2 pi r. Now, why didn't I just say it's going to be exactly the same number? The R is different. Very good. The current's the same, but the R is different. So that's going to be 4 pi times 10 to the minus 7 times the current, which is 2 amps, divided by 2 pi times the radius, which this time is 0.04 times the square root of 2. Okay, so let's see what we get for this guy. So that's going to be 2, so 4 times 10 to the minus 7 divided by 0.04 times square root of 2. So I'm getting 7.07 times 10 to the minus 6. And what are the units? Tesla. Very good. But this time, though, you can't say that it's in the positive x direction. You can't say that it's in the positive y direction. Do you agree with me that this vector has a little bit of x and a little bit of y in it? Do you agree? You now have to find out how much x and how much y does it have. So in order to do that, let's imagine that point P is actually the origin. And that's your x-axis, and that's your y-axis. So you can do something like this. Now take a look at the following. Do you agree with me immediately that this angle should be 45 degrees? Why? Because that's a square, and that's the diagonal. So the diagonal bisects that 90-degree angle. Does everybody agree? Immediately then, you should be able to know that this is also 45 degrees, because the x-axis is perpendicular to the y-axis. Does everybody agree? Now, then from there, you should be able to say that this angle here is also 45 degrees. Why would that angle be 45 degrees? Well, because this vector makes a 90-degree angle with respect to the radius. Does everybody agree? So then, if this is 45, this has to be the rest of the 90-degree angle, which is also 45. Now, again, because the y-axis is perpendicular to the x-axis, this also has to be 45 degrees. Does everybody see why this angle here is 45 degrees? And why do we need that angle? The reason we need that angle is because now we're going to break that vector up into its components. So look at this. I'm going to just draw that vector by itself with its tail originating at the origin. Would you agree with me that I need to break that up into components and I need this angle, which I just figured out is 45 degrees? Does everybody see that? So now, take a look. Do I know the magnitude or the hypotenuse of that vector?
Yes.
What is the hypotenuse of that vector?
That's 0.07 times 10 to the minus 6.
Excellent. Tesla. So now I can calculate the x component of magnetic field 3 and the y component of magnetic field 3. So in order to do that, the x component, it's going to be adjacent, right? So that's going to be cosine. So 7.07 times 10 to the minus 6 Tesla times cosine of 45 degrees. And the y component is going to be 7.07 times 10 to the minus 6 Tesla times the sine of 45 degrees. Does everybody agree with that statement? Okay. So now, I can write the B3 vector collectively as something in the x direction plus something in the y direction. Does everybody agree? So this would be the x component here, the coefficient of the I hat. This would be the y component. So what is 7.07 times the cosine of 45? What does that give?
5 times 10 to the minus 6.
Excellent. So 5 times 10 to the minus 6 Tesla in the positive x direction. That's symbolically the I hat direction. And in the y direction, I get exactly the same thing. Okay, so does everybody see how I got this vector here? Does everybody see how I got it? So now, what would be the next step? I have all the magnetic fields. What do I do with them now? I add them together. So this is the superposition principle that I was talking about. So the net magnetic field, so I'll call that B net, is equal to the vectorial sum of all of those fields. So in other words, B1 vector plus B2 vector plus B3 vector. So that means that I'm just going to add these guys together. So that's going to be 1 times 10 to the minus 5 Tesla in the j hat. Is that an x component or a y component, by the way? How do you know? J hat. J hat is symbolic for the positive y direction, right? So plus B2, what's my B2? That's that guy. 1 times 10 to the minus 5 Tesla in the I hat. Is that an x component or a y component? How do you know? X because it's I hat, right? Plus, this guy has x and y together, because remember, it was diagonal. So let's take a look at that guy. That guy was 5 times 10 to the minus 6 Tesla in the I, plus 5 times 10 to the minus 6 Tesla in the j. So to add the vectors, remember you can only add like components. So add the x's together, right, to get your net x, and then add the y components together to get your net y. So when you do that, you get 1.5 times 10 to the minus 5 Tesla in the I hat, plus 1.5 times 10 to the minus 5 Tesla in the j hat. So this is going to be your B net, your vector. but it was asking for the magnitude of the net magnetic field. How would I find the magnitude of the net? This is just the vector itself. How do I find the magnitude of a vector? I have to do, yep. So square root of the x component squared plus the y component squared. Does everybody agree? But now here's the thing. Here's a trick. Does everybody agree that both of them are the same? The x and the y components are the same. Does everybody agree? So that means you have a 45, 45, 90 special right triangle on your hands. So it's easier than that. It's just one of them times the square root of 2. You know how for 45, 45, 90 right triangles you have A, and then the hypotenuse is A times the square root of 2? It's the same kind of thing. Now if you want to, you can plug this all into your calculator. You can say this squared plus this squared all under the square root, and you get this. So now if I actually get a decimal for that, so 1.5 times 1.41, so that gives me 2.12 times 10 to the minus 5, and what are the units? Tesla. So that would be the net magnetic field at that point. All right, so does everybody see how we got it? Now, no one asked me the following question. Does it matter which corners are occupied? Imagine if instead of this one would have been occupied, and I wanted to find the magnetic field here. Would that affect the magnitude of your final vector? It will not. It will affect your direction, but it will not affect your magnitude. It will be the same. Okay. All right.